Hello? You're looking at CT scans of a patient who's bleeding in their brain. Those who survive this often face a further complication where their arteries in the brain restrict. This is called vasospasm, and it often isn't diagnosed in time for effective treatment because we don't understand the causes underlying it. In this and many other areas, there's pressing need for causal discovery to help us uncover the underlying causal relationships in data. But in practice, causal discovery is often hindered by heavy reliance on human experts. They have excellent sources of domain knowledge, but they often aren't trained in causality, and this can make eliciting their expertise very difficult. And furthermore, they're very expensive, their time is very valuable, they have a lot of other things to be doing. So there's great potential to try to tap into LLMs as experts in their place. Like humans, they have a lot of background knowledge, and unlike human experts, they're readily available. But the catch, of course, is LLMs are potentially unreliable. So in my current research and under guidance of my supervisor, I've been looking into ways to mitigate this unreliability and tap into the potential of LLMs as readily available experts to enable scalable and practical applications of causal discovery. So in the rest of my talk, I'll address a few key questions, first with some recent research results and then with some preliminary results of my own to try to establish how we can do this. First, by addressing what kinds of causal discovery questions we can pose to LLMs, when we should ask them, and finally, how we can, under these constraints, still hope to uncover new relations that we wouldn't have found without the LLM's help. So, what kinds of questions can we ask? Many approaches to using expert knowledge in causal discovery rely on specifying particular edges or edges that aren't present in the graph a priori. But there's a good argument in a recent paper against doing this with imperfect experts like LLMs. And I'll relay the basic intuition to you with a simple example. So suppose we have a basic graph, just two nodes, education and happiness, and some link between them indicating that our education impacts our happiness. But we introduce a third node, income, and it turns out this breaks the direct link. Instead, education is impacting income, income's impacting happiness. And this indicates the problem: you can't decide on direct edges in a graph without considering all of the other nodes in the graph. For complex domains, this quickly becomes infeasible. But if we restrict ourselves to a causal ordering question, that education has some impact on happiness, but not necessarily a direct one, this is a much more reasonable question to ask. So we want to ask causal ordering questions, but when should we ask them? And you could, in principle, ask between every pair of nodes in the graph, but this is very computationally expensive. This is what the last paper tried, but they had a lot of issues in doing that, trying to mitigate the expense, trying to deal with inconsistent responses. But there's a lot of work with data-driven algorithms in causal discovery over the years, and it would be great to try to use LLMs to augment what already is there. And we can follow a basic deduction to do so. If a data-driven approach can detect an edge, but not the orientation, and an LLM can give us the causal ordering, then we know that should be a direct edge in our graph. And this can arise pretty commonly in existing approaches. For example, constraint-based algorithms always recover a graph that isn't fully oriented. Score-based approaches can often have a tie between one orientation or the other. So these are two natural opportunities to try to use an LLM. And a recent paper tried this approach with score-based algorithms. But there's still a catch here. We might be orienting the edges better, but we're not necessarily finding anything that wouldn't have been found in the base algorithm. So this is what I'm working on now, to try to use LLMs as judges to help mediate ensembles of these different algorithms. As I hinted at, we have constraint-based algorithms, score-based algorithms, many others with different strengths and weaknesses. And we can have occasions where different algorithms seem to detect an edge but not agree on the orientation. And this is a great opportunity for an LLM to try to step in. And some preliminary results on common benchmarks against a standard ensembling method are promising at the moment. This scoring metric is called the bounce scoring function, but higher is better. So we've seen we want to ask causal ordering questions when there's uncertainty, and that by trying to use LLMs to mediate ensembles, we can hope to uncover new information and data. And altogether, this establishes the potential to use LLMs as experts in causal discovery, but with care. And the hope is that by developing these techniques further, we can apply them to complex real-world cases like vasospasm. Thank you.